Hi there, my name is Logan Boyd. I am a senior in mechanical engineering, and I've spent the last couple semesters working with Dr. Ram Iyer in the mathematics department to design custom contact lenses to correct higher order visual aberrations with the MATLAB program. There are two steps to my research. The first step is to design a contact lens correction for up to fourth order visual aberrations. With a conventional lens, you address the second order visual aberrations, astigmatism and defocus. These are the aberrations that are correlated to near and farsightedness. Now, for most people, if you address these second order aberrations, it's sufficient. But for others, the higher order aberrations are significant enough that they cannot see unless you address them. So the first step is to design the correction. Once we've done that, the second step is to meld that correction into the rest of the patient's trial lens so that we have a nice smooth surface that is safe and usable for the wearer. Now, who can use custom vision correction? Short answer is everybody. The theoretical maximum for this vision correction is 20/30 vision, which is much better than I currently have. You can imagine there are many people that can benefit from custom vision correction: pilots, air traffic controllers, even professional athletes like baseball players who may want to see the spin on a baseball as it comes out of a pitcher's hand. But for our current research, our particular target need is keratoconus. Keratoconus is an eye disease that is characterized by an abnormally thin cornea. That thin cornea can bulge outward and cause visual symptoms like streaking. Those symptoms are on top of your regular astigmatism and defocus, so your regular prescription contact lens cannot address the symptoms. In addition, because of their thin corneas, these keratoconic patients are often ineligible for eye surgeries like LASIK, which remove corneal material. So these people are effectively blind and have very little they can do about it. To give you a visual aid, here are some Logmar eye charts that you might see at your eye doctors. On the left is keratoconic vision after applying the best currently available conventional second order contact lenses. How many lines can you read? This vision is obviously terrible, and even worse in the right, which represents a nighttime keratoconic vision. So this is a very significant problem and one that we need to address. You might be wondering, if contact lenses have been around for decades, why hasn't this problem been addressed beforehand? Well, simply put, the technology to manufacture these contact lenses are very, very recent. Rigid gas permeable contact lenses, like the ones we intend to create, have been around since the 70s. But those contact lenses were conventional lenses with uniform curvature. These were relatively easy to cut with lathes. The higher order aberration control contact lenses have very unique front surfaces which are more difficult to cut, and the lathes that can do the work have only recently become available. Currently, keratoconic patients wear scleral lenses, which cover the whites of their eyes. And while these lenses protect their cornea, they don't do anything about higher order aberration control. While rigid gas permeable higher order lenses have been tested beforehand, they are far from being commercialized, which is our opportunity. That's the background. Let's get into the research. First of all, we need to understand how to mathematically characterize a wave of light. When light enters the eye, it gets refracted and distorted into a wavefront. That wavefront can be completely described by a set of Zernike polynomials. Each Zernike polynomial describes a unique aberration, and the coefficient for that polynomial describes the severity of that aberration. If we have all the coefficients, we can understand exactly what happens in a patient's eye and therefore how to correct. How do we get these coefficients? Hartman Adverometry. During an Adverometry test, a patient will wear a trial lens, and a beam of light will be sent directly through the center of their eye. That beam of light will then reflect and propagate back out through their eye, creating a wavefront. That wavefront passes through an array of lenses, which then projects that light. Based on the scatter of that returning light, the Adverometer will calculate the Zernike coefficients, which we can then use to reconstruct the wavefront of light that your particular eye creates. Now, there are some challenges with Adverometry. Unlike an MRI or an X-ray, Adverometers take multiple readings over a period of time, and no two of them are the same. If a patient blinks, the lens may rotate or slip, and even if they don't, your pupil is constantly adjusting, constricting, and dilating to adjust to the amount of light coming into your eye. So all those readings will be over different pupil radii. The question is, how do we account for these errors, and how do we create a single representative wavefront to use for a correction? Let's take the first error first. We need to calculate lens rotation and decentration. Our MATLAB program allows the user to select points on the lens and on the pupil. The program then identifies the pupil in a blue circle and the lens in a red circle. Additionally, the yellow line indicates how much that lens has rotated on the patient's eye. When we understand how much the lens has moved and how much it has rotated, we can account for that in our correction. Secondly, we need to address the different pupil radii. Before we average our wavefronts, we need to rescale all of our wavefronts to a single consistent pupil radius, and that is what you see here. We begin with a wavefront over a radius of 2.2 millimeters and redefine it over a radius of just 2 millimeters. Once we have resized all of our wavefronts, we can create an average wavefront. This is the shape we will add onto our patient's lens to create the correction. On the right, you can see the standard deviation. The dark blue represents a low standard deviation, so you can tell that the center part of the lens is very accurate, and we lose accuracy as we depart from the center. This accuracy determines how large we can create the correction over, in this case about 2 millimeters. Now, in adding the correction onto our patient's lens, we create a new problem. There is a dislocation, an edge, if you will, between the corrected and uncorrected portions of the lens. That's due to, again, adding material for the correction and creating this step discontinuity right at 2 millimeters. This is a major hurdle to higher order design. At best, this edge could cause some irritation, but at worst, it could even cut the patient's eyelid, which is a huge problem. So we need to solve this obstacle before we move any further. Our solution to this obstacle is the cubic spline interpolation. This interpolation will span the corrected and uncorrected regions of the lens, and it will match the values at those two radii and the curvature of the lens at those two boundaries. This will smooth over the two regions and create a nice smooth front surface for our patient's lens. Here is the interpolation numerically. Interpolation begins at the inner 2 millimeter radius for our correction and extends to an arbitrary user-defined outer radius, in this case 3 millimeters. Once we have created our interpolation, we will then insert it back into our patient's trial lens, shown here. As you can tell, the edge continuity is almost completely eliminated. The danger is gone, and our patient can finally safely use our corrected lens. Now we've done all the hard work. We have gathered the data, we have accounted for errors, we have resized, we have averaged, we have added the correction and smoothed the lens. What is the final result? On the left is the same logmar eye chart that I showed you at the very beginning of the presentation. This is the best that a keratoconic patient can see with a current conventional second order lens. On the right is how well they can see with our fourth order corrected custom contact lens difference. Can you see the difference? Let's talk about the impact on the field. Like I mentioned beforehand, higher order control really isn't possible until you have a method to smooth the corrected and uncorrected portions of the lens. Without that interpolation, commercialization is impossible because the lens is not safe. So this interpolation method really is an enabling technology. Now, currently, if you go to your eye doctors, you will be diagnosed with an eye chart. Perhaps you will be matched with a contact lens that fits your eye as close as possible. But in the future, we envision that your eye doctor will use an adverometer to measure your eye directly and create the front surface of a lens that can correct up to fourth order aberrations for your particular eye. Match that with a device called an optical coherence tomographer, which measures the contour of your eye, and you will be able to design the back surface of a contact lens to match the surface of your eye precisely. So instead of finding the closest contact lens, the best fit power, we can actually design a custom fit and custom correction lens for every patient. My contribution to this research has been to read the literature and the code written by Dr. Iyer and his previous students over the past 8 years, and integrate, comment, and debug nearly 1,000 lines of code. Perhaps most importantly, though, for the first time, we have used actual patient data from keratoconic lens wearers and created a new custom design for an actual patient. This means we are truly one step closer to actually making blind people see. All of this would not have been possible without academic support. I am extremely thankful to the undergraduate research program and to Dr. Iyer for steadfastly supervising my research. And finally, thank you for listening. If this research is interesting to you, I recommend the following works which have guided my research. We are all indebted to the hard work of previous researchers. So thank you very much again for investing your time in this program and in this research. Take care.